the University of Twente, the control laboratory is located within the Electrical Engineering building. Inside this laboratory, research is carried out on the subject of advanced control engineering. In order to test more advanced controllers, a number of experimental setups were built. One of these setups is the one-link flexible beam. This setup consists of a motor and a long flexible beam, which is mounted on the motor's axis. One of the goals of this setup is to move this beam such that the response of the tip is fast and has almost no overshoot. To achieve this, a conventional axis controller is insufficient. If such a controller is applied, then the vibrations in the beam are not well damped. This results in an unwanted large settling time and in overshoot. In order to damp these vibrations well, a number of strain gauges were placed along the beam. By use of the strain gauges, the vibration can be measured and counteracted by a state feedback controller. If such a state feedback controller is used, then the response of the tip is fast and contains no overshoot. Now, a payload with mass 0.5 kilogram is attached to the tip. The obtained response shows overshoots and an increase in the settling time. Hence, the response of the tip is deteriorated. In order to have adequate control, overshoot should be avoided. One way to avoid overshoot is to design a controller, shown as CR, which is robust against the variations in payload mass. If the payload mass is 0.5 of a kilogram and a robust controller is used, then the tip response contains almost no overshoot. When the payload is removed, the obtained tip response by the robust controller will also show almost no overshoot. However, the settling time has increased significantly. Another option is to design a controller for each payload mass. If the beam has to transport payloads, as shown, then two controllers can be designed for these masses respectively. If the mass of the payload is known, then the controller related to that mass can be selected. In practice, the mass of the payload is generally not known. This implies that no selection between the controllers can be made. In order to make a choice between one of the controllers, one can make use of a supervisory control. This requires that for each mass, a model is available. For example, M1 and M2 donate the models for different payload masses. These models can be run in parallel with the process. By comparing the process outputs with the different model outputs, a detector can decide which is the best model. The controller related to this best model is then selected. In order to apply this approach, use has been made of fast parallel hardware, that is, transputers. In this case, a board with 7 transputers has been used. Application of supervisory control to the beam with no payload shows that the response is fast and has no overshoot. Application of supervisory control to the beam with payload mass half a kilogram shows that the tip response is fast and has almost no overshoot. Supervisory control can also be applied to non-linear processes, such as a 2-link flexible robot arm. For instance, the linearized dynamics encountered at 0 degrees is different from the linearized dynamics encountered at 90 degrees. The process is controlled with a controller which performs well around 0 degrees, and if it is desired that the robot lower arm should move from 0 degrees to 90 degrees, then the response shows a large steady-state error. If two controllers are used related to 0 degrees and 90 degrees, then by switching between these two controllers, a response is obtained which shows almost no steady-state error. Supervisory control is applicable in practice and gives an increased control performance.